video illustrates the simulation of a bridge rectifier circuit using Multisim Live. Here I've already connected the circuit diagram in Multisim Live, and I've changed the settings for the input source to 10 volts peak 40 Hz according to the circuit schematic in the lab sheet. And I've already placed a voltage probe at the output, and I've labeled it as Vout. The next step is to choose the simulation type as transient, and then to choose the end time from here. Finally, we're going to click Run to run the simulation and look at the output. We're going to now click on Split so that we can show the graph here as well as the circuit. Notice that the purpose of the bridge rectifier circuit is to convert the AC signal into DC. So far what we've done is we kind of like cancelled out anything that's negative and took its absolute value, except notice that Vs has a peak value equals to 10 volts while the output voltage has a peak value equals to 8.64 or approximately 8.6. So according to calculation, according to the formula in the lab sheet, Vout is supposed to be the peak value of the input, which is 10, minus 2 times Vd, which is 1.4. Remember that Vd is 0.7 because it's the voltage drop across the diode. So Vs minus 2 Vd is equal to 8.6 volts for this particular circuit. And here we've got a value equals to around 8.6 as well. Now, to improve this bridge rectifier by reducing the ripple voltage, notice that this is the ripple voltage here. This is equal to 8.6. So to reduce it, what we're going to do is we're going to connect a capacitor in parallel with this R. And then we're going to start with a value equals to 10 microfarad for the capacitor. Now we'll rotate it and then connect it in parallel with the resistor. Next, I'm going to run the simulation again. Observe what will happen to the ripple voltage. This is now my new ripple voltage. It's been clearly reduced. And notice that initially we're starting at a value equals to 0, and then until we reach 8.6 approximately. And then the voltage at the output drops a little bit, but it doesn't reach 0 again because we have now a memory device, which is the capacitor. Since it acts as a charger, it will charge first initially, and then when the capacitor here discharges, it doesn't discharge completely to 0 volts. That's why the ripple voltage improves at the output. Now, to measure the ripple voltage, what we're going to do is we're going to place cursors. So to do that, we're going to simply click on the signal itself, the plot, and then choose the type of the cursor to be track. And then we're going to place 2 cursors so that one of the cursors, or cursor number 2, is at the peak of the output or the maximum value of the output, and cursor 1 is at the minimum value of the output, ignoring the first minimum because here we're just starting actually. Now what will happen here is that delta Y, which we can read from here, is going to give us the value of the ripple voltage. So notice the improvement in the ripple voltage is now 1.5 volts instead of 8.6 volts earlier without having the capacitor connected.